The following is a production of the University of Minnesota.
Introducing Mark Ahlstrom. So Mark has been the CEO of WindLogic since December of 2000, and under his leadership, the company became an authority in the assessment, forecasting, operation, and integration of renewable energy. WindLogic became a subsidiary of NextEra Energy Resources, which was formerly FPL Energy, in 2006, allowing it to expand its role as an applied R&D center and provider of services of utility, wind, and solar energy clients. Prior to joining WindLogic, Mark was founder of two software technology companies, and the most interesting thing about Mark is he holds his degree in biochemistry and biomedical engineering from the University of Wisconsin-Madison. I had the opportunity of attending Mark's lecture last year in the Wind class, and it was brilliant. So I give it over to you, Mark.
Well, pleasure to be back with you here. This is the first time I've done it where you've already, I guess you're supposed to have already looked at last year's lecture. So what I thought I would do is actually kind of do a review of some of the highlights of that lecture for the first half here, so you can address any questions you have. So feel free to, if anything you don't understand in some of these points, let's get right into questions. We'll talk about that for the first half. And then as time allows for the second half, I actually wanted to get kind of farther afield into areas that kind of interest me personally, that kind of follow from forecasting as we get more into power markets and the, how we're going to actually put wind energy and solar energy to some extent fuller into the markets as we get to higher penetrations, so that we can actually make the whole system work and how that works. So a little bit view of overall power system operations, power market operations, and maybe even a little philosophy stuff toward the end when we get into discussions about, how should we actually be funding a lot of the R&D that's going to advance forecasting in the future. So feel free to interrupt me at any time as we go through some of this. As you already know to some extent, WindLogic was actually a supercomputer company who got into weather modeling many years ago. It used to be that you had to have a supercomputer to run a weather model. Now we run them on racks of standard processors in a data center just like everybody else. I joined in 2000, and it was kind of a restart situation because they had a lot of very high-resolution weather data and weather modeling that they were using for environmental problems. And we started applying it to wind energy about 2003. We were acquired by NextEra Energy. They are the largest owner, operator, developer of wind plants in North America. Now, companies like Xcel actually buy a lot of that power. So Xcel is the utility that buys and distributes the most wind energy. But in fact, they buy a lot of it from private, what they call independent power producer companies, like the half of NextEra Energy that I'm with that does power projects all over the country, sells that power. Today, WindLogic is about 65 people. About half of them have a degree in meteorology or physics or related field. Another 25% of the remainder are like applied math, stats, computer science people, IT. I spend a lot of time with engineers. I do have an engineering degree, not in anything I work in, but we spend a lot of time personally with electrical engineers, with market designers, you name it. Now it's a very multidisciplinary field. If you haven't figured that out already, when it comes to using wind energy, and we actually, since we're now part of a large utility company, we do a lot of other optimization problems, more than just exactly where to put wind plants that we're talking about here today. But overall optimization of the utility system. So what that means is I'm easily distracted to talk about anything you actually want to ask about in the entire field. But what I'll cover today is kind of a quick review of resource assessment, forecasting, a bit about the solar energy and climatology issues for the first half, and then we'll get more into these other topics as we have time. So this was the movie I like to show. And you saw this probably when you looked at last year's lecture, but just to highlight here, the particles, the colored particles, are the wind speed at about 100 meters above the ground where the wind turbines exist, right? And they're color-coded, so when they turn like the red hot colors, they're very high-speed winds. Blue colors would be slow. And what you see here is, constant variability, right? And you also see, as we're showing from some of those shaded and isobar areas, those are where jet stream patterns are actually driving a lot of the energy down to the surface by spinning up a low pressure system like that right there, and really creating a lot of that energy that's brought down from the upper air winds down to the ground. I went into more detail in the lecture last year about how, everybody thinks that the winds just propagate along at the surface. So all I have to do to forecast the wind here is have a measurement tower 30 miles upwind, and that's what's coming to me. In fact, that's not the case at all. An awful lot of the actual energy comes from vertical phenomenon in the atmosphere, where it's more about, how much of that high-speed wind from above is actually mixing down into the turbine blades. But you certainly have a lot of variability to deal with here. And if you're trying to figure out, where am I going to plant, $500 million worth of turbines, and I can't move them for the next 20 years, and you're stuck with what you got to get pretty good at convincing the bankers that put up the money that you understand enough about this that you know what the production is going to be. Similarly, when it comes to the operating, more the forecasting and how it's put in the power systems, the utilities are very concerned about this variability for the reliability of the grid. So you've got to help them deal with how you're going to schedule that variability into the power system. So the real challenge, of course, is that all power plants are dependent on their fuel source. The fuel source for wind energy is wind. If this was a natural gas plant or a nuclear plant or anything else, it has its own concerns about its fuel supply, and the fuel supply often dictates a lot of the characteristics of the energy that comes off of the plants that use that type of fuel, right? So in this case, we've got these implicit characteristics of wind energy, which are, variability and uncertainty. So how do we understand it and actually engineer it so it's useful to people? Now the complexity comes in because the winds are often very impacted by the terrain, the location, the roughness, even whether the leaves are on the trees or not, right? All of that impacts the wind speed in this lower level of the atmosphere where what they call the boundary layer, where the weather hits the surface of the earth. And not to make matters even more complex, a pretty small difference in wind speed is magnified because of the power curve that you probably saw some of this last lecture. There's a cubic effect between the instantaneous power that comes off of the turbine and the wind speed change, right? And now we love it when we're forecasting and the winds are blowing so strongly that you're up on that flat part of the power curve, because it can go for many changes in wind speed. The power is already maxing out the generator. We know exactly what the generation is going to be, right? Unfortunately, as you may have heard, turbines are actually engineered and designed on purpose so that you spend most of your time on that steep part of the power curve, because that's where you get the most energy for the dollar invested in the turbine. And so we're usually dealing with this cubic effect. Literally, people complain if we're off by 0.2 of a meter per second in wind speed, which is nothing from a meteorology point of view, but it makes a pretty significant difference in the power. Also, we've got this variability in all time scales, whether it's just the pattern through the day, the change over the month, the seasonal patterns, the year-to-year variability. Wind speed increases with height, as you may know as well. But exactly how quickly is it going to go up today based on the situations today and the thermal stability, all these sorts of things. Very complicated to actually figure out exactly what's going to hit the turbine. So that's where a lot of this challenge comes from. And this is done, of course, for the bankers, as I mentioned, for the operators, and just basically to figure out the best places to put these projects and how to use them. So the traditional way of actually figuring out, first of all, where you're going to build the plant before it even exists is, you go off, you put up a met tower, a meteorological tower. Usually it's a 60-meter tip-up tower, has measurement instruments on several levels. And you measure the wind, hopefully for at least a year. So you understand, at least for that year, what is the energy, at least at 40 and 60 meters, right? Now the trick is a couple things. First, you've got to extrapolate that up to hub height. And the turbines are not at the 60 meter sort of heights of most of the met towers. They're usually up at 80 or 100 meters today, right? So you've got to figure out how you're going to extrapolate that up. And then you got the problem a very big problem, that year I measured is not necessarily a typical year. There's enough year-to-year variability that it's a very difficult process to figure out, okay, we measured that year, but what's the next 20 years really going to be? What's the typical year and the range of years going to be? And so the way they've done that historically is called measure-correlate-predict. Very simple old school engineering sort of method. You measure for a year at the site you want to build. You figure out what you think the wind speed is at hub height there. And then you say, well, how can I actually figure out if that's a typical year? So you correlate it with a longer term reference, usually like an airport, where they have weather stations set up there for long periods of time for measuring the weather for aviation. And you assume that you can find essentially a linear correlation between that in some form. You use that to kind of extrapolate out and say, what's the normal year and what's the kind of the 20-year pattern likely to be. I pointed out in the lecture you saw before that there's a lot of challenges with that, right? Because you have uncertainty in where you measure. You don't know how to extrapolate that up. You get icing. You don't get great data. And then, of course, the airports are put where it's not windy, like down in the valley, 30 miles away, and the wind plants are intentionally placed at the windiest spot you can find, usually up on a ridge line or an elevated area where wind speed is amplified as it flows over a ridge or something. And the diurnal pattern down at 10 meters is just the opposite of what it is up at 80 meters, as I went through in last year's lecture as well, right? We live down here by the surface, where it's nice and calm in the morning and it gets windy in the afternoon. The turbines exist up above, where it's actually windier at night in general and less windy in the afternoon because of the way all this friction mixes up to the blades. So it's a challenging approach here. So the method we've used for a lot of this now, as we get more of this more advanced weather data available to us, is to say, yeah, let's go ahead and let's measure at that site. On the ground measurement right there is great because that's a ground truth. But let's not ignore all of this other weather data that's available today. So we bring in all of these weather data sets, that are used for forecasting and for climate change and everything like that. We use these advanced models to actually fill in the gaps in space and time and really understand how everything we can about that site for at least a year in great detail. We then use some of the longer-term climate change data sets to get a better reference that's better than those airport towers. And we actually use very advanced physics modeling that we'll talk a little bit more about when we get to the forecasting session to really take advantage of all available data. And by the time we're done, we're really trying to create a full-blown physics simulation of exactly what would that wind plant have produced in power if it had already been there for the last 20 years. And you have to do that with computer modeling to generate all these data sets and actually look at the layout of the turbines and everything like that. So that's kind of a quick summary here of how we go through all this. By the time you're done with looking at all the data you measured on site and that you can model, you then have the issue too of, okay, I understand the wind really well, right? But that's not necessarily what the turbine's going to produce, right? Because it's not just one turbine all by itself. You're going to put out, in most cases, dozens or even hundreds of turbines. Now, each turbine, of course, takes the energy from the airflow, and it leaves kind of a wake behind it where there's lower energy because I just sucked a lot of the energy out by that first turbine. So it's going to be less windy behind it, right? So depending on the wind direction, depending on how you laid out the site, you're going to have what we call wake losses, which are going to vary based on the direction of the wind that day. You're also going to have, sometimes the turbine is not 100% working. So you have an availability deduction. You have, the power curve is, supposedly guaranteed by the manufacturer, but, not every turbine performs exactly as specified. And then you've got electrical losses, just going from the turbine to where it connects to the grid in the collector system, as well as changes in the airfoil. As it ices, it gets ice on it, it gets dirty. It doesn't have the same lift that it did when it started. So all of these things can contribute to losses. So even though the wind may say theoretically I can get this amount of power, the amount you actually get out is often going to be 12, 15, 20% less than that when you look at the overall production of an entire plant. So by the time we're done here, pre-construction, what we really try to do is figure out, do I know everything about how I think this plant is going to work? Where is the power going to come from? Which direction? So I can optimize how I lay out all the turbines on the site. I understand the wind distribution as well as I can because two sites with exactly the same average wind speed may have a different distribution of when those wind speeds occur. How much do I have of each speed, right? And because of that nonlinearity of the power curve, that distribution, it makes a big difference. So two sites with exactly the same average can have completely different power output because of just how that distribution happens to fall relative to the power curve of the turbines you're using. And by the way, we actually run a site when we're running it here. We model it down to like 30 meters. We run it with maybe 10 different models of turbines. We look at different layouts every time we change a layout because of any change in the site. We completely have to rerun all that and try to optimize, how we're going to get the most out of the available land with the turbines we have available, or the type of model of turbine that we think is best, and come up with a bottom line number of power on this. Okay, so what are the questions? Pretty quiet crowd here today. So this is all, basically you're doing this before you ever even break ground on the site. You maybe put up the tower. But this is the basis for how you do the design of the wind farm, how you get the financing, and how you determine how much power you're going to have to sell to some utility or some off-taker to make the money for the plant. Anybody got questions? Yes. It varies a lot. In this part of the country, or through most of the Midwest, the strongest winds actually tend to be more in the winter and the shoulder seasons, and the summer actually gets relatively less windy. And the reason for that really is that a lot of the energy is really driven by those big storm systems that we saw, and we tend to get more storms the way the jet stream sets up. More of the storms track across us, as you may know. More in the late fall, the winter, the spring. When you get a lot of those storms coming through, things like that. The summer, you get more of the jet stream shifts, farther north. It brings less storms through our region. We tend to get more high pressure. Those sunny days, the nice sunny days tend not to have as much energy in them, really, in terms of wind energy, because the storms are not coming through and bringing a lot of that down to the earth. So there's a lot of variability. So we see kind of a pattern where it will be highest in the winter and kind of dip down in the summer and then go back up again in terms of the month-to-month variability. Any other questions on how we actually figure out the pre-construction assessment? Yes, ma'am.
So when you're doing your site, do you generally have choices for your drawing, or is the location kind of preset by where?
Yeah, the question is when we're designing where we put the turbines on the site, do we have a lot of choice, or is it all predetermined for us? A little both, actually. Usually the developer of the project only has a certain amount of land where they have agreements, usually with the landowners, to use their land for the wind plant, right? And so you're constrained by the boundaries of that property area that you have to develop. You have setbacks where you can't put it too close to roads or houses, or for noise you have to set back and so forth. So you go through a process initially of looking at the land available, the number of megawatts or turbines that ideally you'd like to get in there, and then you start based on our wind data, we'd like to start doing what we consider to be a pretty optimal layout. Where do I want the turbines based on the available space that's left after all of those setbacks and everything. Now, that doesn't mean it doesn't change all the time, because one landowner may want 2 turbines on their land, and there may be all sorts of complexity, or often the perimeter of the project will change over time as landowners come and join, or leave the agreement. So we try to do it in an optimal way to kind of maximize the energy production. But it doesn't always work out as optimal as we'd like, because sometimes you end up packing the turbines closer than ideal, just because you have limited land. If we were trying to maximize the amount of energy we're getting off of it, we would spread them out a lot more. We decrease those wakes, but that's not a luxury we always have. So it's not always ideal by the time you're done. Yes. Yeah.
So I'm clarifying. My understanding is that when wind goes through curve, it slows down you're
right.
Yeah,
the question is really, how do you space these, and are you trying to maximize energy or megawatts capacity? The general rule of thumb is that you don't really if you know the prevailing wind direction is like from the west, you don't like to place the turbines closer than about 5 rotor diameters on the north to south direction, and no closer than about 10 rotor diameters or farther on the east to west direction, right? So you can pack them closer. If you got a real, a site that has a real predominant wind direction, as long as they're perpendicular to that wind direction, you can pack them relatively closely. But then you'd really not want to have them too close on the downwind side, because you do get a lot of loss from the wick, and you don't want them to all line up the way you design them. But like we're talking, it's far from ideal in terms of the amount of space we actually have for that. But yeah, people do come in already saying, this is going to be a 100 megawatt project, no matter what, and you kind of have to do the best you can to lay them out, even though you know that you're going to have higher wake losses in that case. That make sense? Okay. Any other questions? Yeah.
How much fidelity do you model in terms of turbine? So if you needed to pack them closer, you model, for example, the controller might suboptimal to reduce the weight loss.
Yeah. Well, what we do is, we actually work with the turbine OEM, the manufacturer of the turbine, and we typically will have to give them some of this wind data, some of this turbulence data we measure, and the layout, and we'll work with their engineers to say, do you certify this turbine for site, site suitability, right? Because they do get concerned. If it's a high wind speed site, you're packing the turbines too close, you're going to throw off too much turbulence. That downwind turbulence will impact those turbines and put more stresses on the gearboxes and so forth. So they get concerned about mechanical warranties on their equipment. If you're packing them too tightly, or if the terrain is very complex and generating a lot of turbulence as well. Is it a full-blown modeling? Not in a full-blown CFD, aerodynamic sense. It's more in a kind of a rules of thumb about how much turbulence do you think is going to be at this site, and are they comfortable with the spacing? Yes, sir.
If the wind speed is variable by height, would it make sense to put different size?
Yeah, as far as the tower height. Yeah, the question is if since wind speed tends to increase with height or vary with height, does it make different heights even within a same project? There are people experimenting with taller towers, especially at lower wind speed sites. Typically around here we've been putting in turbines at 80-meter hub heights, more or less, lately. There's one that's just going up, I think, 120. They're doing some, cement towers up to 140 meters, over in Europe. Because obviously, if you go up higher, you get, on average, higher wind speeds. You have to weigh that increase in energy against the additional cost, materials of the project to do that. You're asking too, does it make sense that I'd have one tall tower, one shorter tower? People have looked at that. I'm not aware that it's widely used yet, because you think, well, I can kind of tuck a turbine underneath the other one, kind of thing. You have some turbulence concerns with stuff like that as well, especially under certain wind directions. So it's not widely done, but people are talking about it. Yes.
Do you guys do any offshore projects? And if so,
Yeah.
does that change a lot for the whole process?
Yeah, the question is, do we do offshore projects, and would you change how you approach the project? We have done assessments for offshore projects. There haven't been any built in the United States yet. There's some that are getting close. The challenge with offshore, first of all, is it's harder to measure on site, of course, because you're off in the middle of the ocean. So it's very expensive to put up a tower where you can measure. Some people are putting like LiDAR or SODAR devices, that can be on a buoy mount or platform mount, and trying to do that. That's tricky too with wave action and everything, as you can imagine. So they try to get some onshore measurements. They try to go through a pretty similar process of at least trying to model. And modeling is probably used even more offshore, just because there's less actual measurement data off there. So it's pretty similar. It tends to be a smoother surface with less roughness, and so the shear may actually occur a little bit sooner offshore, where you don't have to go actually as tall with the tower above the ocean level to get to the same shear benefit. And the wind speeds tend to be good. The challenge with offshore, of course, is not only is it more difficult to do the assessment and measurement out there, it's a lot more expensive to put in the foundations, to get out there to do the O&M. So the general rule of thumb is that the cost of offshore energy, wind energy, is still a lot higher than onshore. Several times higher by the time you figure out the additional costs of the assessment, the construction, the maintenance. The advantage, of course, with offshore is that it tends to be closer to the coast where more people live, and the prices of power is higher. So you have to weigh that off against, do I build cheaper wind in the Midwest and build more transmission lines, or do I spend a lot more for my wind and offshore and connect it, directly into New York City or something like that? My preference, I tend to think if you really want to do the maximum amount of clean energy for the average citizen, you would build a lot more transmission and a lot more wind power in North Dakota, Minnesota, in this area, and be shipping it around the country. It's not easy to build transmission lines, of course, with the permitting and how people feel about that. So it's still a lot of give and take about which direction the country is going in terms of, land-based wind versus offshore wind. Anything else on this? Great. Okay, let's move on and talk a little bit more about wind forecasting then. Just review this very quickly. We pointed out that, if you want to actually run these models to generate a weather forecast, whether that's with, forecasting and running it out for tomorrow or using historical data to do this sort of assessment, you've got a very complicated physics problem here. There's a lot going on. Wind energy essentially is solar energy, if you think about it, because the winds are produced by differences in pressure. The differences in pressure are largely produced by differential heating of the surface of the Earth by the sun. And you do this in a thin layer of fluid wrapped on a spinning globe, right? And that's where the complexity comes from. So any sort of temperature difference, all these things produce changes in wind speed. So how do you start? What you do is you really divide that up into this three-dimensional matrix so I can put it on a computer and start to model it, right? And that gives me this grid, which is the starting point for, trying to figure out what is the state of the atmosphere right now. And the way we do that, if you're running a weather model, is you say, well, I don't have measurements at every corner of every grid cell there that I'd like to have. But I do have quite a few measurements out there from all the weather stations, from balloons they release, from aircraft that take a profile of the atmosphere as they take off and land, satellites, all sorts of stuff. So there's thousands and thousands of weather measurements that are made, every hour. And they tend to be shared pretty widely in the weather communities around the globe. So based on the measurements that are there, you can use physics to say, is there a physically consistent state of the atmosphere that would account for all these measurements I do have, right? And that gives you kind of this, what they call the initialization data set, the starting point for what's the best snapshot I have of the weather system right now. And then if I want to run a model, what I do is I take that starting point as time zero, and I say, well, I understand a lot of those other physical problems that are going on, all those changes from the incoming solar radiation and everything. I can represent those as partial differential equations, essentially creating a physics-based simulation model. And I can say, given that starting point, can I step it forward to the state it's going to be 10 seconds later, 10 seconds after that? And that's really what a weather model is doing. It's just a state transition of saying, I know the starting point, and I can use physics to estimate the future points. So if I run that out for tomorrow on a bunch of computers, that's where the forecast comes from that is used by the weather person on TV, right? And once you have, that wind speed data at the location, which you can pull out of that sort of weather model, I've got a pretty good forecast of what the wind speed and other weather variables are likely to be at the location of my plant, right? If I want to turn that into a wind power forecast, it's a whole other beast, right? Because even if we know the wind speed perfectly, we still don't know how much power is going to come out at the meter, at the point of interconnect. There's two ways you can attack that forecasting problem, as I talked about last year. One is probably the most intuitive way. You say, well, I do have that Met tower usually at the large wind site. And I've got, I may have my year of data of that. And I'm using often these weather forecasts that come from the Weather Service. I could have an archive of what those were every day for the last year as well. And I could find the relationship between the wind speeds that I observed and what I actually saw the models telling me, right? And they may not match exactly, but there's certainly going to be a correlation there. If I find that relationship historically to allow me to predict wind speed at my site from the weather models that are available, and then I take that and I go through a turbine power curve, or I have a way of deriving what I think the overall plant power curve is going to be, and I convert from wind speed to power, right? Very intuitive, and a lot of the wind forecasting vendors out there do use a method like this. Although others in the wind power forecasting community said, that's great, but I've got uncertainty about how I do this relationship to wind speed, and then I've got additional uncertainty about how I convert wind speed to power. Is that really the best way to get to the most accurate wind power forecast? Or what I really care about, of course, is what's the power at the meter? Do I just focus on that? And that's where this other method comes from of directly training to power. And basically you're saying, I don't even care about what the wind speed is at my site. I find the relationship between what the weather models tell me and what the power is at the meter that I'm concerned about forecasting. And I directly find that relationship. And then when I want to actually use that historic relationship in real time to produce the power, I just go directly from the new forecast through that relationship to get the power forecast, right? So both of them come out with a power forecast, meaning, how many megawatts every hour for the next 24 hours kind of stuff, but they do it in different ways. The other issue we have is that we often have more than one forecast, right? And we also want to use not just a single variable from these forecasts. We actually want to use maybe the forecast points all around our site in a 3D kind of way, because not all of these are direct, simple, linear relationships. We actually want to use a lot of the variables and find the complex nonlinear relationships. So how do you do that? You got 3 different forecasts. They don't all agree with each other, right? But they all tell you something. And maybe one of them works better under certain circumstances and the other works better at another time, or maybe the combination of the two can average together. You need to come up with some way of combining those. And what we really use for that are machine learning methods that are able to find these complex nonlinear relationships between these very complex weather model outputs and the power coming out of the wind plant. And so you can actually do that. Even if you just do a simple average of multiple weather models as an ensemble, it tends to be better than any individual model. But you can do a lot better than that if you start using support vector machines or computational, artificial neural networks or something like that to actually optimize and find these real relationships. And that's where a lot of the applied math sort of people in our group come in. And from that, based on what function you're optimizing with your machine learning methods, you can minimize error, or you can work on preserving the distribution or finding ramps, depending on what you're trying to optimize. So you actually come up with a better forecast than by using multiple forecasts. And then if a new forecast comes along, or a change, an additional model, you can add that in and get even better. And the other thing you get out of this, of course, is that because we now have kind of multiple opinions, we can tell, how confident do we think we are in that forecast. There are circumstances where all the different models, each of which is using a somewhat different physics or different initialization data set or something, if they all agree, we're pretty sure that the weather system is very well understood and well modeled, and you can have high confidence in it. If they diverge, the extent to which they diverge is at least one indication that, well, this might not be a real predictable weather pattern. I might be less sure about that, right? So you end up actually nowadays with not just a deterministic forecast, but a distribution around that, a confidence interval, prediction interval kind of confidence sort of band around that. And that's useful because, we can actually provide the utility operator now with a forecast that shows, how confident are you? Does that increase in certain weather patterns? How quickly does it increase as you go out in time? Of course, it also depends on things like where are you on the power curve at this moment, because that, an uncertainty in that wind speed will be magnified if you're on the steep part, but less magnified if you're on the flat part of the power curve and so forth. So all this turns out to be useful as we bring more and more of these probabilistic methods into how we actually use forecasts and how we operate the system. So as we talked about last year here and what you looked at, it's not just a single forecast anymore. It's using multiple weather forecasts. It's using some fairly sophisticated computational or learning system or statistical methods to pull all this together. And I also should mention persistence. If you're trying to predict what the wind plant's going to produce 5 minutes from now, what it's producing right now is about as good a forecast as anybody can do, right? Because the wind speed really doesn't change very quickly. People think it does because we feel these short-term gusts as you're standing outside. But when you really look at the overall energy in a larger, going through that entire swept area, there's a lot of mass there if you actually start averaging out these little gusts from the turbulence. The fact is, it doesn't change very fast, and so it's tough to beat a forecast of persistence for the next 20, 30 minutes even. And so you start blending that in, where you use persistence for the very short term, and then you start blending in the models and get the best of all that as you go out. And as far as how well it does, for a single wind plant, we're seeing typical errors expressed as a percentage of the nameplate of the wind plant day ahead of maybe 12, 14, 15% today. Meaning if it's a 100 megawatt wind plant and you want me to tell you this morning what the power is going to be at 2 o'clock tomorrow afternoon, the average error of that forecast would typically be, plus or minus like 12 megawatts, 12%, right? Now, as you get closer to real time, it gets a little bit better, like for 4 hours ahead. As you get down to like 30 minutes, 15 minutes ahead, it gets a lot better once you can start using persistence, where it would be like half of that, right? Maybe 6%. The other way you get a lot of benefit is by aggregating these forecasts. Instead of looking just at one wind plant, can I actually pool together 12 different wind plants that are spread over Minnesota and North Dakota, right? As you do that, you cut down a lot, not just the variability, but also the uncertainty around the forecast, because a lot of the uncertainty in the forecast is like timing of exactly when is that weather system going to move through, and not all wind plants see that at the same time, things like that. So you get rid of roughly half of all of that variability and uncertainty if you just put it into a large enough power pool. And in fact, MISO, the Midwest Independent System Operator, is doing that right now with their centralized forecast, and they're reporting that their day-ahead forecast overall is right around 6%, right about what you'd expect for a larger area. Now, people are always saying, the problem with wind forecasts is they're so bad compared with load forecasts, because a load forecast for tomorrow might be, like 2% error. And, I always say, well, that's great, but you really have to compare it not against the 12 or 15%. You have to compare that against, a 6% number, because that's an entire system load forecast. You have to look at an entire system wind forecast to do an apples-to-apples comparison. When you look at it that way, wind is still, tougher to predict than load is, but it's not an order of magnitude different. It's getting in the same range. Of course, there's a lot we're also doing to improve this, because they care not just about the averages, they care about, when are the rapid changes, those ramps going to occur, things like that. So a lot of research going on with that. I mentioned this project that we have with the Department of Energy when I spoke last year, in which you probably saw. We're starting to wrap up an analysis of an entire year of forecasting, where we're using a higher resolution forecast from NOAA, the National Weather Service. We're giving them some of our additional data to see if that improves the model when they incorporate more of our data into the forecast. And what we're seeing is that, all these things help a little, right? None of them are a slam dunk, but as you get more data into the forecasts, more sharing of data from wind plant operators, for example, that's probably going to help some. As you go to higher resolution models, on faster, bigger computers, that's going to help some. If you can just turn that forecast around more quickly so it's available to us faster, that helps for improving the forecast for the next few hours. So everything helps, but nothing's going to suddenly cut the forecast error in half. We're going to keep working on this just to keep nudging it down and see gradual improvement over time, and it is in fact happening. That's kind of a summary of what we talked about, and what you already saw from last year's lecture in terms of more the operational forecasting. What questions do you have on that? Yes.
When we use the wind forecast to calculate power forecast, do we assume that our blades are being actively pitched for maximum efficiency, or do we take the average amount?
Yeah, question is, do we assume that the blades are essentially automatically for us going to be optimally pitched and so forth? Obviously, additional information from the wind plant does help us do a better power forecast in terms of, which turbines are not running today, the availability. Is there curtailment already being done on the power, for other reasons? So we have, we like to get that information, do a better forecast. In general, though, every turbine runs individually with its own control system. And although we are doing research on, should you be looking at more optimized plant-level control, reality is most of them today run kind of as an independent entity where they're just looking at what the wind speed and direction is that's hitting that turbine, and the controller in the turbine is automatically then setting all the pitch angles and the yaw and adjusting it. So the turbines are kind of on their own, with their own little computer system. They're adjusting, where they're steering into the wind. They're changing the pitch to accommodate the wind speeds that they're seeing, at the instruments that are right in the top of the nacelle of the turbine itself. So usually we just assume that the control system is doing its job and optimizing power to the power curve as best it can. Now, you see, if we're using the type of forecasting where we're not really doing the wind speed to power conversion, though, that sort of complexity is picked up. It's learned automatically when you find the relationship from the wind speed, weather models to the power, right? So you're kind of learning the personality of the plant for all these different weather conditions when you look at it that way. So as long as the turbines behave relatively consistently, that will be picked up in these computational learning systems and reflected in the power forecast optimization that we do. Anything else? Yes?
Do you take care about the for service on the wind farm?
The question is forecasting used to determine when we're going to shut down a turbine to repair it and do the maintenance? Yeah, to the extent that they can, they do. They try to schedule the maintenance for low wind speed periods. Sometimes, we know, in the summer, it's going to be generally less windy. So major maintenance where they have to take turbines down for several days and do a whole bunch of, repairs that they can put off, they'll often put off to the lower wind speed months. But they will look at the weather forecast or our wind power forecast, and when they can, they'll try to identify, this would be a good day to go up in the tower and do this, or, this is going to be a high wind speed day, and if I don't need to shut that turbine down yet to repair that bearing or something, let's let it run through this period. We'll sell the power. We'll shut it down next week and get that done. They try to. Yes.
Correlation between the forecasting errors and supply for growth. So they really care about is matching supply and demand. So even if you have forecasting errors in wind, it's somehow balanced by their errors in the consumer.
Yeah, your question is about more on the power system operations, about how do they balance, forecasting error against load error. Yeah, let me get to the more the power system operations section where I'll talk about that in some length if I could, and we'll go into that. Yeah, very interesting topic. Anything else right now? We can take more later. Okay. And let's talk just briefly on the solar energy topic. I know it's not the main emphasis here, but a lot of when it comes to integrating and forecasting solar is a similar problem. These solar plants, of course, get to be pretty big. 25 megawatt AC side solar plant here covers 180 acres. And unlike wind, where you can kind of graze cattle right up to the tower, it pretty much uses the whole thing. So this is the challenge when you do these utility scale solar plants that are most commonly done out in the Southwest. They cover a lot of space and they pretty much use up the land. When we're doing an assessment of solar, it's a little bit different, and it really depends on the type of solar technology. Because if it's any type of solar energy that's going to focus the beam, whether that's a concentrating thermal solar or a concentrating PV, it really can only accept the direct beam that comes from the sun because you have to focus it, right? Whereas the more common PV that you may be more familiar with, it doesn't care where the photon comes from as long as it somehow hits the panel. So if it bounces off of a cloud, if it bounces off of haze in the atmosphere, that's okay. This is a little more tolerant in terms of doing the assessment because in both cases we care about how much solar radiation is going to be available to us, but things like haze or humidity, things like that make a lot more difference if it's a concentrating technology. The other thing that's interesting with solar is that, unlike the wind, we can't see the wind. It's the clouds that really impact the solar forecast. And you can see the clouds. You can see the shadows of the clouds here over that same PV plant. And so the trick with solar, the main driver of the solar forecast is, can you actually forecast clouds? Things like haze and other things like that are of secondary nature, not nearly as important as the cloud patterns. Now, sometimes, actually, from geostationary satellites, you can see here's a cloud bank that's headed toward that plant in South Florida. And if I have a snapshot from these satellite images every 15 or 30 minutes, I can actually infer the wind speed vector from that. And assuming those clouds are stable, I can project that forward, and I can say, I know about this time that cloud is going to pass over this site. So this satellite tracking is a great method, especially in the time range of the next few hours, out to maybe 4 hours or so, for certain types of clouds. Now, it's not going to work for convective clouds like thunderstorms, which essentially pop up out of clear air from other causes. So it's not perfect, but it helps. So we really find ourselves using a combination of techniques when you come to solar forecasting. You'll use this sort of satellite or even direct observation from the ground for the next few minutes, but then you have to drop into those same sort of weather models when you go up beyond about 4 hours. And certainly if you're trying to predict, tomorrow, you get into that same problem of using these weather models to really forecast. Now the challenge is that clouds are very tricky. You don't know exactly where they're going to be in many cases. And it's not, these convective ones are very tough. We know you might have a higher, chance of a thunderstorm tomorrow, but you never know exactly where it's going to pop up or where the cloud will be. But you do the best you can with this. And some of these high resolution models are certainly useful, but even they can't directly model, day ahead exactly where clouds are going to be or exactly where thunderstorms will pop up. What you do hope to do, though, I think, is giving information to a control room operator saying, well, I might not be able to tell you exactly, when this nice puffy cumulus cloud is going to be over your plant, but I can tell you that, we're going to have a stratus deck tomorrow morning, or we're going to have a marine layer that's going to be kind of that flat gray clouds in the morning, right? And I think that's going to burn off about 10 o'clock, right? I expect that to burn off. And then it's going to be pretty good for a while. And then, we think we're going to start seeing these cumulus clouds building up from the thermals. And they'll start out small. So you'll see these small peaks, and then they're going to get bigger and denser. So you'll see these deep peaks. So I'm maybe not predicting exactly exactly when the cloud's going to be there, but I'm kind of telling you kind of that distribution, right? That standard deviation, what you can expect in terms of the amount of variability you're going to have to deal with. But I think it's stuff like this that's going to be useful to the control room operator, even if it's not a perfect forecast. And the other thing to keep in mind is just like wind, geographic dispersion, as we talked about with wind, very important point. It really reduces the variability and uncertainty. Same thing with solar, even more so. If it's a partly cloudy day and you got these solar plants spread out, they're not all going to see the clouds at the same time. So if I've got 16 smaller sites as opposed to even one big one, it's going to smooth out very, very quickly. So although solar, a utility room guy looks at stuff like this, it drives them crazy because this is a huge amount of variability to put on a power system. But when you actually start looking at it at a system level, again, it gets much less scary. Right? They're still scared about it, don't get me wrong, because they just aren't comfortable with a lot of variability to start with, but it's not going to be as bad as people think. Now, the real debate, of course, with solar is, where are we going in terms of what types of solar we're going to build? Are we going to do a lot of these large utility scale projects, either thermal or PV, or are we going to do mostly distributed rooftop, IKEA store kind of stuff like we're seeing around here these days, right? And obviously, from the point of view of a control room utility who's taking the power, they both have their advantages. Centralized, it looks more like a conventional power plant. We've got visibility because we can afford to put in a lot of instruments and meters. We can control it at a substation. We have the economies of scale, so it's actually cheaper to build overall if we do central station in terms of dollars per megawatt. So in some sense, they like this better. But distributed also has its advantages. Utility doesn't have to pay for it. A lot of it is done by the homeowners who want to put solar on there and are just willing to do a net metering sort of deal. It's usually more distributed, although you do get neighborhoods like this around San Diego where it's a wealthy neighborhood. Everybody in the whole place puts it on. It becomes a pretty centralized plant in that sense. So there are advantages both ways. The real disadvantage that we see with some of the distributed is that our distribution system, meaning those lower voltage lines that deliver the power out to your homes, were never really designed to move a lot of power back up the other way. The assumption when these were built was that it was all going to be produced at a big coal plant. It was going to go over transmission wires. It was going to go to your local neighborhood and was going to go out in the distribution system. And so there are cases where they're having to limit the amount of distributed solar they can put out there just because the local transformers, the local substations can't safely handle that or have to be upgraded to handle more power that might sometimes be flowing the opposite direction. And the system was just not designed for that. So a lot of give and take. I'd say at the moment the PV and probably the distributed PV kind of has the more momentum right now. Although we're involved with building some absolutely gigantic PV and concentrating solar projects, meaning like 500 megawatts of PV, if you can believe it, all at one site, which is a huge, huge project, out in the Southwest. So any questions on that briefly? Just yes.
How does solar generation compare to wind generation as far as do they balance out or
Yeah. Question is how does wind and solar tend to balance out? There is some logic to thinking that they're somewhat complementary, right? First of all, like we've talked about, a lot of the energy from wind comes from these storm systems, these low pressure systems, right? So when it's stormy and cloudy, we tend to have more wind energy around. When it's a nice high pressure system where it's nice and sunny and dry, it tends to not be as windy, but it's sunnier, right? So overall, from the storm system point of view, they tend to be somewhat complementary. Obviously, in a lot of places, the wind speed falls off in the afternoon, whereas solar energy picks up in the afternoon. So they tend, on average, to kind of be quite complementary. They're not perfect, however, because like in California, they see like the PV solar, the distributed solar, actually starts. Sun starts to go down really. 3, 4, 5 o'clock at night. It's headed down. So solar peaks earlier in the afternoon. But the actual peak load where they need the power is usually later in the afternoon when people are coming home from work, starting their dinner, doing all this. So you still see that PV is not a perfect match to the load patterns in a lot of places, but it does tend to have, what they call higher capacity value in terms of its match with load than wind does at a lot of sites. So they are complementary. You're still going to need some other flexibility, other sources of flexibility to fill in the gaps. We'll talk about a bit later. Anything else on solar? Must have been a tough week for you guys so far. You're pretty quiet here. Okay. Okay, let's talk just briefly on climate. We'll go through this. We'll probably take a break, and then I'll actually get into some new material that will get you going a little bit. Climate is what you expect, and weather is what you get, right? The climate's the long-term average, the expectation for this time of year. But the weather signal is extremely noisy on that, right? There's a lot of weather variability that goes into those long-term averages. So we get into climate science, climate change. It's very difficult for everybody to separate out the weather variability from the true climate signals. Now, there are some interesting climate patterns that come into play when you're dealing with wind energy, for example. And a lot of this comes from the fact that you may have heard of like the El Nino cycle, the ENSO cycle. There's actually like dozens of these different climate cycles that people are observing out there. Some of them may be just statistical interest, but others of them do have a very significant impact. Now, what they fundamentally are, for the most part, are results of lots of energy being stored in the oceans one way or another, and then kind of re-expressing itself into the atmosphere in different ways, right? And the most common of these is the El Nino cycle, the ENSO cycle, same thing. What happens is, depending on how hot the Pacific Ocean is, that heat creates a thermal high, right? A pressure difference from that heat, right? That heat actually it's such a huge high pressure system, it actually diverts the jet stream patterns, right? The jet stream patterns are going to steer around that big dome of high pressure. It's the jet stream patterns that steer a lot of the weather systems, which generate a lot of the wind energy that hits the turbines, right? So, what we typically see are typical jet stream tracks across the country like this in normal years. You can see they shift a little bit from summer to winter, and there's kind of two typical patterns. The more stable one is that one coming across our area from the northwest. We often see these winds from the west-northwest around here, right? But you'll also get into these storm tracks sometimes, like a big blizzard track where, they'll say, oh my God, the jet stream shifted south. It goes to this track. It pulls all of that moisture up from the Gulf. We get our big blizzards in the winter, things like that. So it's often in one of these two patterns is the predominant pattern. Well, what happens when the El Nino pattern shifts the tracks, it splits the tracks, and we don't tend to get this crossing through the country anymore. We actually get more wind and more rain like down in Florida than we typically would during an El Nino year, but we have fewer storm systems going through the center part of the country on average. So, El Nino will tend to decrease the amount of wind energy we see in a lot of our wind plants. Now, keep in mind, this is a tendency. This whole thing maybe accounts for 15% of the energy we're talking about here. The rest of it is this noisy weather pattern, right? So even during an El Nino pattern, we can have one month that's just, great wind energy and another that's bad. It's the weather variability can completely overwhelm all of these different patterns. And most of the climate indices patterns are much weaker than the El Nino is. So this is one of our stronger ones, right? And to make matters worse, of course, all these patterns are on different time scales. Like the Pacific Decadal is, roughly a 10-year pattern, but not exactly. And El Nino comes and goes. You never know when it's going to be here. Now, you may be able to predict it a few months ahead. Everybody thought there was going to be a strong El Nino that coming up this winter again. It's already looking like it's fading out. So every model was saying we're going to have one. Now we're not so sure. So this is pretty complicated to figure out. But the bottom line is you do get this year-to-year variability like we were talking about. And, this is looking at the top here is, looking at the last, the 30-year sort of pattern. So you see this long-term average, the red line, the P50 is the long-term expectation. But because of this variability, there is uncertainty around that. And you're going to see, like 1 year out of 100 would be down at the purple line in the bottom instead of up at the average line, right? So we talk about this, these P50, P90 values. You see the same thing here, by the way, with solar, right? This is looking instead at the months of the year. Every month has a same sort of distribution. And, our production for any given period, might actually be more like this on a wind site around here, right? We have this long-term average, but we've got that uncertainty around it. And from one month to the next, it will bounce around where it's, much higher than normal one, it's lower than normal. Here's one that's, like a 1 out of 100 sort of year, right? All within a typical year. So even though we try to get the average right, you're never going to get, know exactly what, how much power in July versus August, but the envelope in which it's likely to fall. So that's where we come up with this, the P50 is the long-term average expectation, kind of the deterministic value you expect as a P50. But we often talk about a P90 or a P99. P99 would be kind of a 1 year out of 100 at the bottom level here. Now the bankers, of course, tend to take a lot more looking at the P99 because they don't want that first year, to just happen to be so low you can't afford to pay them back right out of the box, right? So often you'll only get financing for a more conservative value, but the long-term expectation would be the P50 value. Any questions on that? Yes.
So you guys
Yeah, well, in terms of when we go back and we look at how did the last year do, then we actually do try to extract out these El Nino type events. And we do use that. We do like a longer term forecast where, the weather models really only work out for about 2 weeks maximum, right? And they're only good for about a week maybe before chaos takes over. And so those models should have already reflected a lot of this jet stream pattern type stuff, right? So in terms of the operational forecasting or just what's the power going to be tomorrow, usually that's just already kind of embedded in the models. But when we're trying to do a forecast like we do for people say, well, what's the next 3 months or 4 months or 6 months going to be? Then we will put in a note that says, yeah, this is looking like a strong El Nino season, so we would expect to be about 20% lower than normal. However, we always put a disclaimer: weather's weather. It doesn't necessarily mean we're guaranteeing that you're going to be that way, because, like I said, even in that strong El Nino, you might, the weather patterns can overwhelm that, and you actually get more production than you expected. So you try, but the El Nino only counts for 15 or 20% of the total variability you're seeing here. So it's not a very good forecast. And nobody wants to talk about climate change. Oh, yes?
It sounds like there is much concern on that about the situation, 20% of power. But is there more concern now about the general placement of wind turbines based on climate change?
Yeah, the question is there a concern about where we build wind plants based on climate change? I probably used this line last year too, but everybody asked me, is climate change going to change where the winds are? Is it going to be higher or lower at this spot? I would say, yeah, it's going to be higher or lower at that spot, but I have no way of telling you which, right? Because it's going to, if you change, the big tipping point for climate change would be if it permanently changes some of those jet stream tracks, because then our storm tracks, storms tend to follow those jet stream patterns. It would completely change the occurrence, the chance of storms events, which would change wind, precipitation, you name it, right? We haven't yet reached a tipping point where we see a permanent shift in jet stream patterns that doesn't come back, from these climate indices and things like that, but it could happen eventually. The problem is, if you're going to predict at a certain site how it's going to change, you have to predict where you think the future jet stream patterns are going to be and how that's going to impact all those weather systems. And right now, they run huge ensembles of these long-term climate models. They run them out for years. And they'll run a large ensemble of them, dozens of these. And they'll tend to have these spaghetti plots that will kind of cluster around certain patterns, but you always have other ones that are completely in a different place, So it's very difficult to tell at any particular location what the long-term consequence of climate change would be. First problem, of course, we have to get everybody to actually agree that climate change is real, and maybe do something about it, but that's more of a political issue than it is a scientific one, I guess, at this point. So, the best we can do is, we're not going to change our decision too much about where we build wind plants today. Would some of them be in the wrong place if we had a major shift in some of these jet stream patterns? Absolutely. I guess we'd have to build new ones someplace else. What I'm going to do now is expand on things I mentioned in the last year's lecture, but I wanted to go into more detail on some things that are of special interest to me. I started out actually doing a lot of this assessment work and the forecasting work, and then another thing we did early on, going way back to about 2003, was generating these historical data sets for wind integration studies. Back then, Excel was very concerned about how much wind energy can we put in Minnesota before the cost of using it is just too high. So we generated these time-synchronized, like 3-year data sets of modeling wind energy, extracting out as if you already had all these virtual wind plants, all these places, gave them, 5-minute sort of time series for 3 years, and they kind of ran their whole grid with and without the wind energy on it to see what the challenges would be to integrate wind into the system and what they thought it would cost. To understand that, let's go way back though and just start out. What exactly is a power system? Historically, of course, people had houses and they said, well, I'd really like to start, having electricity instead of kerosene or whatever in my house, right? And so they would build a local power plant, for just their city usually, these municipal type plants, and they would connect it directly to the local houses. And this works great to start, but then you get, a whole bunch of these cities around, and they say, it's kind of silly that each of us is independently having to balance and have all of the extra, reserve energy we need for reliably keeping the lights on, when if we connected ourselves, we could actually share that because, I only need this once in a while, and if you can help me when I need help, and I'll help you when you need help, you can reduce everybody's cost of operating your system, right? Because rather than having everybody, sub-optimize their whole system and have all the extra reserves they need for keeping the lights on in emergencies, they can pool that. They all save money, right? More economic. And this is really the synthesis of this. None of these power grids we're talking about here started out as a big system, state or multi-state plan. They all started out as individual municipalities. And it's just been kind of a hodgepodge of starting to connect these for reliability and for economics. And they've ended up on their own connecting themselves, right? But we don't have really even a state plan, or let alone a national plan for how the power grid really is designed. We've gone to higher voltage lines to connect these regions for reliability, but most of it's been driven by reliability, not by clear design or even economics as far as that goes. The other issue we have is that, if you look at this system demand, we were talking about, what's the power I need at any instant. The amount of load, the amount of power they need really varies through the day. And you typically see, kind of this, a two-hump sort of pattern. You got quite a bit of power and people get up and everybody turns on their lights and does their showers and breakfast and stuff. During many types of the year, unless there's a lot of air conditioners on that are pushing it up in the afternoon even more, it may actually, go down a bit in the afternoon and then pick up again in the evening. So a pretty typical pattern. So the way that the generators have built all the generators that they need, the power system operators have built the generators, they say, well, this is a pretty predictable pattern, at least for this season of the year. So if I want to economically provide a match for this, I might have some nuclear, I might have some coal that I run all the time, right? Because that's my base load. And then I might have some hydro I can squeeze in there or use, and then I'm going to fill in a lot of these ramps with like combined cycle natural gas plants, which are maybe more expensive than coal, at least used to be, but I can start them and stop them every day. Whereas a coal plant, it might take me 2 days to start up a coal plant, and once I've started, I can't shut it down unless I'm going to leave it down for a couple of days, right? Not very flexible. Or nuclear plants never like to ramp, right? And then I have some gas peakers that maybe are less efficient, but they're designed to start real fast and ramp real fast, things like that. I still have this fuzz. I don't have a perfect match, but I'm pretty close with how I schedule all these generators. And then I get an additional sort of service from some of these, like often called regulation, which just says that some of these plants are agreeing that they will follow like a second-by-second sort of signal from me to kind of fine-tune that so that I get an exact match between my generation and my load, right? So I've managed to match this pattern fairly economically. And that works, and I have to keep this in balance. If these things don't balance pretty closely, you're going to get a fall in frequency, the entire system will collapse, you'll have a blackout, right? So it's very important that this is always in balance. Now, suppose you have that same pattern, and you say, well, great, but now I'm going to put a whole bunch of wind on my system. Now, if I look at the net load here, I take the wind energy, subtract it off, and I look at the net load in green about what I have to balance with the rest of my traditional generation. What you see is there's some troubling things initially for an operator. Those ramp rates are faster. It's a steeper ramp in the morning and the evening, right? Because wind might be falling off in general in the morning where the ramp, the load is ramping up and vice versa. It depresses my nice smooth pattern, makes it more variable. And if I look at how I'm traditionally putting my generation on there, I've got some problems, right? My peakers up at the top there, these ones at the very top, they aren't running as much as they used to. So are they going to get paid enough to even stick around? You know, a lot of my gas, way I use my gas plants is different. My hydro, my coal, I'm actually dipping down into that now, where I might have to curtail it some of the time if I want to use all that wind energy. You know, I can't just run it as usual. I need to have really a more flexible system if I'm going to accommodate some of this more variable but clean and cheap, really, wind energy and solar energy. I call it cheap because even though it may be expensive to build, from a marginal basis, once you've got the wind plant built, you know, it has a zero fuel cost, right? The wind is free, whereas gas and coal and nuclear cost money. And so you're almost always going to want to use it once it's built. And so you try to maximize it, but then you've got to figure out what, you know, can I actually run the rest of my system this way? So it really is being a big change in the outlook of the power system operators. They had this nice, simple way of viewing the world, and now we've imposed this variability that actually impacts every level in their nice, simple assumption about how things can work, right? And it really is becoming the biggest catalyst for kind of rethinking how we want to operate our power systems. Now, it's not that this variability is a new thing. The variability was always there. Load's always been variable, you know, but we get enough wind on there, it actually forces us to challenge those assumptions and rethink this and say, is there a better way of doing this? So I start looking at this more as a flexibility balancing issue that allows me to take advantage of as much of this clean energy as I can, and not so much this simple base load kind of view of the world. The other thing to mention here too, I mentioned like that regulation service. You know, most of what we're talking about is energy, but you need more than just energy to run these systems. And with more wind, you know, some of these additional services you need might change as well a little bit. You need reserves for rare events. Reserves are for like contingency events, like if, you know, I always have to be ready for my largest power plant or my largest transmission line to fail. And when a nuclear plant goes or a breaker goes on a big transmission line, I can lose 1,000 megawatts, you know, in a fraction of a second. So I have to have contingency reserves to be ready for that event. I have to have spinning reserve or maybe some slower non-spin for other things, you know, smaller things that change that I have to accommodate. And those are usually kind of, you know, rare special events that I have to be ready for. I also have these ancillary products like regulation or reactive voltage, more complicated concept. I have to support both the voltage and frequency of the system out there, right? And so I need these additional products that aren't really energy products, they're products for maintaining reliability. And I might also have longer-term planning issues around capacity in terms of how do I incent people to build the types of plants I need. Yeah. Suppose that I have to be ready for a mismatch between my generation and load. And some of it I need to be able to react to very quickly. I might have to react to it within like 5 minutes. So spin would be like the gas plants that they already have running that aren't really producing energy, but they're already started, they're running, they're ready to go, and within minutes I can say, I need 100 megawatts from you right now, right? Non-spin would be probably the same type of plants, but maybe they're not started yet, and you say, well, you know, I've got enough spin for the next 5 or 10 minutes, but I know that within 30 minutes I might need somebody to start a plant and give me more. So that stuff that you can start quickly and get online would be non-spinning reserve. So spin would usually be more expensive, and obviously it's burning fuel. Non-spin, you know, might be cheaper, and you know, it's plants that you haven't already dispatched for energy that are available to help you for these other emergencies, basically. And you have to pay them something to be there, right? Because they could otherwise maybe be selling energy or something else. Yes. It could be used as peakers, although you would usually want to be dispatching the peakers. I'll say a little bit more about that. You know, there is an overlap in this. You know, the same units that you are using for reserves, you may the next hour said, I'm actually now going to dispatch you for energy. I'm going to get the reserves from somebody else because I like your characteristics and so forth. But yeah, it's a combination of meeting your energy obligation and having enough flexibility to deal with the reliability if something else doesn't turn out as you had planned it, right? Make sense? So the big question really is, how do we get a more flexible power system, right? And fortunately, there's a lot of things we can do that a lot of people are working on now, and wind has been a great catalyst of doing this. And now you do this stuff, it doesn't just help wind energy, it helps the whole system operate more efficiently. But, wind has really forced them to kind of take on some of these challenges. So they're moving to larger balancing areas. It used to be that, like every city, or at least, even a few years ago, we had 15 balancing areas just in Minnesota. Balancing area is just a kind of a power pool area where you're going to maintain that perfect balance of generation and demand, right? They said, we don't really need that anymore. We're all connected with transmission lines to some level. We can balance the entire state as a single balancing area. Or now we're actually balancing the entire Midwest as a single balancing area. What that means is that for the same reasons that a lot of that power variability, from wind plants went away, because a lot of those differences are random, you might be going up when I'm down, a lot of that cancels out, right? So you end up not having to over-control things. You do less of this regulation. You don't need as much of that. You do less spending things on non-energy type services. And so everybody saves money with larger balancing areas. Similarly, you're concerned about variability if you move to shorter scheduling areas, windows here. A lot of it used to be planned day ahead, a very chunky hour-by-hour plan for tomorrow, very difficult to change. Well, you don't need to do that anymore. A lot of these plants are fast, and I can give you the dispatch for the next 5 minutes, and you can change your power, right? So if I move to 5-minute dispatch as opposed to hourly plans, instantly I get a lot more variability, or a lot more flexibility, rather, out of my existing fleet. I don't need as many reserves. I can just change my dispatch of the energy, and I get a lot of what I need, essentially for free, right? You move that whole commitment process closer to real time. You don't need to plan all the units day ahead. Some of them can be started or shut down within hours or even minutes. And then you start bringing in the load side with demand response. It doesn't just have to be changing a generator. If a load is willing to change the amount of power it uses, that's just as good as a generator. Well, better, actually, because it's often cheaper and lower carbon to just say, I don't want you to be using electricity right now. Can I pay you a little bit to do that? And the smart grid, storage, all these things are part of this improved operations that we're headed toward. In the Midwest Independent System Operator, where we're all getting our power right now, by the way, they're one of the most progressive in this. They do full 5-minute dispatches I'll get into. The other thing we can do is we can start looking at wind plants not just as kind of a must-take generator that we have to work around. We can start saying, wind, we really want you to be an active power plant. So you put in place the electronics where I can actually control you from the control room if I need to. You figure out how you're going to get wind actually into the market, so you're doing a better job of forecasting wind. You're putting it in the day-ahead market. You're a full participant, and I'll talk a bit more about that in a moment. And do you actually dispatch wind? Everybody says wind is non-dispatchable, right? You can't really control it. Well, I'll show you. I actually disagree. And the big thing you do is you start valuing flexibility. You actually say, look, a coal plant that can't ramp is just plain not as valuable to me as a different plant that can ramp, especially if they can ramp economically, efficiently, without a lot of emissions, things like that. And maybe you even develop a new way of looking at ancillary products where I don't need just like regulation and just reserves. Maybe it will make sense for me to actually have a different type of ramping product, not as fast as regulation. It's not second to second. It's more, 5, 10, 15 minutes sort of ramps that I have to follow with wind or with load errors, all that. That could be a new product I'm willing to pay for. Or maybe you actually, in the longer term planning, you say, look, when you're building that new gas plant, please make it more flexible so I can start it and ramp it faster. Is there a way I can incentivize you to actually build a more flexible plant or go back and retrofit your plants so that I can get more flexibility out of them now? I might be willing to pay you for that. Right? It might have value. Now, I'm often asked, isn't the real solution storage? If it's cheap enough, yeah. But so far it's relatively expensive to build and use just a pure, very large storage system, as compared with the same virtual impact I can get from like ramping a coal plant, or getting demand response or something like that, right? So storage is great, And the last time they built a lot of storage was not because they were concerned about all this variability. It was back when they were building all the nuclear plants back in the 70s, and they were concerned about the lack of variability they could get from a nuclear plant, that they wanted to just be baseload plants. And they didn't know how they could possibly integrate a plant that didn't want to vary its output. And now they're all concerned about all these wind plants that, how can I possibly integrate a plant that varies all the time, right? Just the opposite problem. Both of those will benefit from storage. But in general, in all the studies that have been done, it's pretty difficult to put together a business case for saying I ought to build more pumped hydro storage or other large-scale storage at this point. We may get there, and a lot of great research on storage. Prices are coming down. But you don't need storage to integrate wind. It's definitely useful if it's there, especially if somebody else has paid for it. So you still have these ongoing questions, though. Isn't it expensive to integrate wind into the grid? All these integration studies have tended to find that you might need some additional, load following, this ramping kind of flexibility. It doesn't have a whole lot of impact on that very short-term regulation. That second-to-second stuff is not impacted nearly as much as you like. But you might need some other, some additional flexibility reserves of some sort. So often they come up with a number that's maybe, $4 or $5 per megawatt hour, is the cost of integrating, a lot of this wind energy when you get to high penetration levels, which is relatively modest. It's, 10% of the price of the power, basically, or something like that, even if you choose to look at it that way. It's probably better to look at it as in terms of, optimizing your overall cost of serving load for your entire system. And when you start looking at it that way, especially when you start talking about markets, which I will in a moment, you actually find that wind energy probably lowers the price of power and saves the ratepayers money, because you've got to look not just at the integration cost, you've got to look at the impact on the power prices, and how you're actually getting all the energy you need to serve your load. So if you look at it as a total system issue, it's, wind is even more attractive. Do you need a, one-for-one backup? Absolutely not. Where you can incorporate thousands of megawatts of wind with, tens of megawatts of additional, regulation or flexibility here. It's going into a large power pool. You don't really have to look at it on a one-for-one basis. It would be very inefficient to directly try to take wind energy and turn it into a flat block of energy, only to then have to incorporate that flat block into your system like a nuclear plant, right? In fact, the integration cost of a new nuclear plant is probably a lot higher than the integration cost of wind when you look at the impact on the overall system. Does it make it less reliable? Not if you do it right. Obviously, you need system flexibility, make this whole system work. But people were concerned about, just putting in 3 to 5% of wind energy on the Excel system, 10 years ago. They're currently operating here in Minnesota with close to 10% wind. And in some places, like in Texas, there's been days where they're operating well above, 40, 50% wind. In Denmark, they've been over 100% sometimes where they're exporting it. So this is a solvable problem. And you can deal with it at a low cost, of course, if you get a system that really is optimized to be more flexible. And that really benefits the overall system, not just the wind piece. So any questions here on kind of how power systems operate at a very high level? The important thing to look at is, I always say, don't look at optimizing every wind plant. Look at the system you have to run. Figure out how we're going to run the entire power system more efficiently. And, the wind integration essentially just comes for free out of that, as does a lot of other benefits and reductions in cost of the system. Yes?
So right now, does MISO, do they only have a day ahead market, or do they have hour ahead market?
I'll talk about that right now. Yeah, you're always just one step ahead of me, but yeah, very much so. Let's talk about that if people are ready to go on. So now, energy markets. The concept of an energy market, it used to be that all these utilities for each city were vertically oriented utilities, meaning that they were responsible for generating the power, transmitting it to the load, delivering it down to the load, collecting the bills, the whole thing, right? Well, a few years back, we said, well, really, it makes more sense if you want to get more competition and more sharing these larger areas to separate that. So you've got generation on one hand, you've got load on the other, and then you've got the transmission system, the high voltage transmission system in the middle, which really should be kind of run as essentially a public good, like a highway system, right? And that's usually now being operated in about 60% of the country anyway, by these, what they call these independent system operators, which are usually nonprofit groups. The utilities and everybody else are members, but their job is to run the transmission system in a fair and open way so that any generator can sell power in and any load can buy power they need, right? Now, the way that the other thing they run, though, in order to do that fair and open transmission access, they usually run a market, right? Because they want to optimize the cost of producing the power and how it's going to get to the loads in the lowest possible cost. What you do is you usually create a power market, and that's usually run by the independent system operator. Now, there's two types of markets you can start to have. Often people start with just a real-time, within-the-day market, right? The utilities might still schedule their generation for tomorrow, but then when it comes to what I'm doing today, if I'm a little short, I'll go to the market and I'll buy what I need. If I'm a little long, I'll sell that extra power into the real-time market. So that's typically what they call the real-time market, is sometimes called the day one market. Now, most of them, like MISO, Texas, California, New York, have also now gone to what they call day two market, which includes that real-time market, but it adds a day-ahead market, which says that I actually want to do what they call day-ahead unit commitment that's more economic in nature as well. In other words, all the generators are going to say, tomorrow I am offering to produce up to 100 megawatts of power at $50 per megawatt hour, right, for that hour. All of them will put in a bid like that or an offer like that. The market operator will say, we'll look at the load forecast for tomorrow, and they say, well, I actually need, 10,000 megawatts from my market, right? They'll look through the offers, and they'll start by taking the lower priced ones, and they'll go up that price offer stack until they get enough power to meet their load for that hour tomorrow. And that's the price at which the market clears. Now, the interesting thing that's probably not intuitive is they clear this market by going up that bid stack, and everybody gets paid the highest price that they had to go to for that day, for that hour, right? I had to go up to that, maybe that $80 generator for that particular hour. Everybody, even though you may have bid in at 30, you get paid 80 because you're all contributing to help me meet that load for tomorrow, and that's what that is worth for me, right? So it clears at the marginal price. Now, you also create, that's your energy market. You also create these other markets now for ancillary products, like regulation, like spinning reserve, so forth. Those are separate markets in a lot of these now that are also paid for by the system operator. And the important thing now, of course, is that what this means, because you've kind of deregulated this market, I don't have to be a utility to be a generator anymore. I can just be a generator. And I can have somebody else that's delivering to the load, right, that does the distribution side. And any generator, whether it's owned by a utility or an independent company, can become a market participant, can make these offers, and get free and open, open and fair access anyway to the transmission system. And so the generators offer in, loads buy out with their bids. The system operator financially spreads all the money around so people get paid for what they do. And what that does is it really optimizes the entire system, because the lower cost, more efficient generators are used first, right? And the amount of load you need is acquired for you. And so a load-serving entity doesn't really have to worry about doing generation if they don't want to. The next step of that is that there's a concept here called locational marginal price. Now, when at the top here, we say if there's plenty of transmission, then I'm going to use the lowest price generators I have to meet my load for the entire system, right? And the price will be the same. If there's no transmission curtailment here, if I don't have any limitations in the amount of power that I can move through the entire power pool, the entire ISO, then I'll use the cheapest generation and everybody will pay that cheapest price. However, there's not, of course, unlimited transmission, or a plant that is here might shut down or not be able to produce as much power as you need. So as soon as curtailment happens, curtailment meaning there's not enough transmission for me to get power everywhere, then the market kind of fragments, where you start doing this optimization at each of these nodes, what they call a locational marginal price node, LMP node, right? And in that case, if in the cases where it's curtailed here, where I can't get a lot of transmission in here, I might not have enough generation over here locally, or I might have to use more expensive generation there locally. So the prices will start to diverge on a nodal basis, trying to match up locally the amount of load and generation that I need. That makes sense? Now it gets kind of complicated. You can go through a lot of examples about, okay, who runs, who gets paid what, but the net effect is that you'll end up with a map of MISO, for example. You can go on their website, you can see kind of this heat map, where you can see what's the price of power everywhere throughout the system. And that's all based on, the price of power that they can get to the loads because of all the transmission constraints out there, and there are many of them. The net effect, though, is that still the ISO ends up doing as optimal a plan as they possibly can, given the transmission that's available, the generators that are available at their bid price, and the amount of load you need, right? So it ends up being a large system optimization, but it doesn't mean that everybody's paying the same prices, and the different nodes might have different power prices that they're clearing at. That makes sense? Now, the question with this is that this market system sounds pretty cool. This is doing a very nice financial market optimization, and I'm just basically selling my power in at one node, and a load can buy it anywhere else at whatever the LMP price is. The problem, of course, is that all the wind that's being done, for the most part, is not really just a merchant generator. There's a little bit of around, but most of it is under long-term power purchase agreements that you'll be learning about. What that is, that's a bilateral agreement where if I'm a wind plant, I get a utility to say they're going to buy all my power at $50 per megawatt hour for the next 20 years, and I probably have some transmission access that I've built to connect from my wind plant to where that utility wants it to be to deliver that, right? So that's a bilateral transaction, or often called a power purchase agreement when it comes to wind power. So how do you put that into a market, right? Well, you can, of course, do what they call self-schedule it in, where you just tell the ISO, look, I'm not even going to bid, but I'm telling you I'm producing power here and I'm delivering it there and I have firm transmission. So take that into account when you're doing your transmission. But if you trust the market, and hopefully you will, you can actually unbundle a bilateral like that, and you can just say, look, I'm willing to just sell into the LMP where my generator is, where my wind plant is, and my load is willing to buy wherever they are from their local node. And my only risk is, do I have a transmission curtailment between me that's going to change the nodal prices? Because if the prices are the same, it doesn't matter, right? I'm done. It's the same as a bilateral deal. There's two things that could happen, of course. One is that the price at the load might actually be lower than where my generator is, more typically, with a gas plant or something. In that case, I would be quite happy, actually, to say, I'm just going to buy at your LMP node for you and deliver that power to satisfy my bilateral contract. I'm going to shut down my generator because I can buy power over here cheaper than I can make it. So I just made money on my bilateral by unbundling it. The other risk, of course, we're more concerned about is, what if I'm selling my power into a cheap node and having to buy it from my load at a higher node? And there turns out there's a way you can get around that in these markets too. You can get kind of an insurance product, usually called a financial transmission right, which basically is a hedge or an insurance to say that if there is a price difference, then this product will make me whole on that. So the net effect to keep in mind is you can take a bilateral transaction or a power purchase agreement, and assuming you have a reasonable amount of trust in the market system operator and the flexibility of the market, you can completely unbundle it, and it still now goes into the market. And what's the advantage of that? Things that are bid into the market are all available to the control room operator at the ISO, who's dispatching all the power plants and all the transmission of the system. And they get advantage of all the flexibility from all those bids to everybody's benefit, right? So it's actually great. And we see a lot of this in MISO now, where people historically have bilateral deals, but most of them are being unbundled now in the market. And so the control room operator ends up seeing and dispatching themselves most of the generation in the system, and that maximizes overall system flexibility. Now, there's other places where, not unsurprisingly, perhaps in California, where it's not working as well. They have a market like this, but for lots of historical and political reasons, a lot of the bilaterals are not unbundled in this way. In fact, some people have projected that maybe only 10% of all the power in California is actually dispatched by the system operator. Makes it a lot more difficult to run a system when 90% of the generation is basically not something you can control. You have a much shallower dispatch stack, they call it, and you give up a lot that way. But MISO is working well. Some of the other power systems aren't working as well at this point anyway. Kind of a strange concept. People understand this, though, that just because you have a market doesn't mean you can't still have one-to-one contracts, and actually they can work quite well if you know what you're doing. MISO is the Midwest Independent System Operator. They run the power grid for the Midwest, everything from North Dakota to Indiana and beyond, Ohio. They're the largest by area, the largest power system operator in the country, and about, I think, the second largest in terms of megawatts, amount of power they handle. So our office is in Energy Park, over here by Bandana Square between the cities here, and MISO actually has one of their 2 control rooms a block away from us there, where they're actually doing a lot of this activity right here in St. Paul. So, as far as getting flexibility, obviously, if the system operator can actually dispatch, the generation and the wind, you can get more flexibility, which is being done. A lot of the ISOs are only expecting wind to follow the dispatch if they have a constraint in their system and they need to curtail wind. They'll more commonly now start doing electronic communications and automatically do that. I'll talk a little bit more about MISO in a moment. The other thing that some of them are doing to get more flexibility is to say, this flexibility is becoming so valuable for me. Do I actually want to do one of 2 things? You can create a whole new ancillary product, like I mentioned before, where you say, this is a new product, I'm actually paying you just to be there to ramp. But you can also change the way you dispatch, meaning you're already in my energy market. I could, if I was looking only at price, I would tell you for the next 5-10 minutes to go ahead and run. But because you're a unit that can actually move, has some ramping capability, I might actually want to hold you in reserve, dispatch a less flexible unit, and pay you the opportunity cost of not being dispatched for energy. So all I'm doing is really changing my dispatch stack, reserving ramping flexibility in case I need it, and making you whole. And that's the way I think that a lot of the systems actually should go at this point, is a good, cheap, fast gas plant is a wonderful thing to have around, but you might not want to only do it for cheap energy. You might want to use it for flexible ramping, right? Now, let's talk about, can wind really participate as a dispatchable generator here? And then we'll get into a MISO example about how they do this. If you were going to do it, what would you do? You'd actually want to bid at least most of your power into the day-ahead market. And the reason you do that is that there's more variability in general in the day-ahead market, right? In the real-time market, I'm sorry. Day-ahead, it's an hour-by-hour plan for tomorrow. Prices are fairly stable, and you can, if I bid in day-ahead, and the ISO says, yes, that sounds good, I'll take it, they're going to pay you whether they need you tomorrow or not. They're guaranteeing that revenue for you. So there's lower risk going in day-ahead. The real-time market might be more volatile, more uncertainty. And so you'll often bid in whatever extra you have tomorrow into that real-time market, but it's good to be in the day-ahead market in general. And then you follow the dispatch signals like we're just talking about, because if you're in the day-ahead market and the real-time market, then you have to follow the dispatch from the system operator that tells you how much power they want you to produce. The trick is, can you get the forecasts to line up with those bidding windows, right? So we can do day ahead, we can do this 12 to 14% sort of error forecast. It's better if we're like 2, 4, 6 hours out, but it's still not great. It only gets really good when you get down to persistence for the next 5, 10, 15 minutes, right? The problem is that historically, most of these markets, even the day-ahead market, was not a 5-minute sort of forecast. You would have to tell them for the next hour what you expected to be able to produce, and you might have to actually tell them that an hour before that, right? So it's more like a 2-hour ahead forecast. That's not so good for wind because you're still in this higher error rate. So what MISO did was actually, I think, very, very clever. They're the only ones that fully has done this so far. But they said that, I can make one change and I can allow wind to actually align its forecasting skill points with this market. And that one change is instead of doing that real-time, hour ahead sort of schedule, I'll let you do a rolling 5-minute forecast. Every 5 minutes, I give you a rolling 5-minute forecast for the next hour. They pull out a value that's about 10 minutes into that because they need to run their process to dispatch everybody back out. They have to run computers to do that. But the net effect is that you're giving them a forecast of the 5-minute period about 10 to 15 minutes ahead of when it's going to start. And if it's an uncurtailed situation and your bid is low enough, which it almost always is with wind, they're, 9 times out of 10, they're going to come back and say, yep, sounds good. I'll let you produce exactly what you told me you wanted to produce. And you're committed then to follow that. If you're outside of about plus or minus 8%, you might have to pay some penalties or make that up, from other, balance it out with other sources, right? But that's not bad. So they make that one change. All of a sudden, wind looks and acts just like a gas plant, right? Except for that one change, they're using all the same processes, all the same software, all the same rules that they would for a gas plant or a coal plant or nuclear plant or anything else. They made the one change that accommodates the forecastability of wind and got it down to the very short-term final adjustment that allows us to run reasonably well within this sort of deadband. Pretty good trick, I think. Wind is dispatchable as long as you define dispatchability in a way that suits the implicit characteristic of wind forecasting and wind variability. Right? Make sense? So I get a little carried away. I think this is brilliant. Because now you've actually made wind a full market participant. Wind bids prices along with this, wind sets prices, and you're no longer being curtailed just kind of randomly because of some transmission constraint. A different, 2 wind plants can be at the same LMP node. One of them is getting a production tax credit and is willing to run all the way down to like negative $30 because they're getting paid the tax credit too. The other one is not and wants to be curtailed at 0, right? Well, if you do it economically where you're bidding, the ones that keep running, the ones that don't shut off first, right? And by the way, I didn't mention, you do get negative bids in these power markets because some of the time we end up with more power than we know what to do with. The price goes negative to, try to convince people to shut down their plants. They don't always do it, but if they don't do it, they're actually paying you to run in order to keep running. But this allows wind to actually be fully financially in this market and operate just like everybody else. Kind of tricky, though. Any questions? Does that make sense? Yeah.
For MISO or any other ICC or God, so do they have like a choice? Like if I'm a private generator, not a utility, can I choose if I want to follow a day-ahead pricing or a real-time pricing, or is it fixed by the ISO?
No, usually you have the option of, you don't have to bid in the day-ahead market if you're a wind plant. Certain types of generators, if they're like a capacity resource, might have a requirement to bid day ahead. But in general, for wind, you don't have to do day ahead. You could, in fact, historically, wind has been a price taker in the market, meaning that they actually just put in a bid that says, I will take whatever the clearing LMP price is. I'll take whatever the market clears at, right? And that's okay. But then the problem with that is that the system operator didn't have any way of knowing at what price did people want to be curtailed if I had to curtail them for other reasons. Does that make sense?
Because if I'm a non-wind generating unit, it's more economic for me to bid in a day-ahead market than real-time market, because then I've promised a particular dollar amount. Your
guaranteed payment for your day-ahead clearing price, yes. Yeah. So traditionally, wind has not been a big player in the day-ahead market, but it's becoming more so, especially if you have this adjustment close to real-time that you can do it. In a well-functioning market, the day-ahead and the real-time prices, on average, are going to converge and be pretty close. There might be more volatility in the real-time market. The average price should be pretty good. So if that's true, in general, you can start getting wind and other variable types of generation in the market pretty well. Yes.
How does a private generator of wind compared to, let's say, Exxon? They have their very expensive ways of selling and buying, selling it for it.
Yeah, some of the wind plants are owned by utilities themselves, and some are owned by independent power companies who are selling to a utility through a power purchase agreement. It's pretty much the same, especially once you're in the market system. Xcel actually operates their Colorado system where they're a vertically oriented utility, and they have a lot of wind out there, but they're not within a market. And here in Minnesota, they have a lot of wind here too, some which they own, some which they buy in both cases. Here they're in the market. They actually find it a lot easier to deal with their wind here in Minnesota because you put it into the market, and the market takes care of so much of this for you. If they're running a Colorado system, they have to do all of their own, balancing of their entire generation fleet, and it's a lot more hassle for them. And they have a smaller power pool in which to balance, and there's lots of reasons why these larger markets are actually good for it. But really, fundamentally, it doesn't matter whether Xcel is the owner of the plant or they're buying it under PPA. Especially once you get to a market system, it all looks the same. They're even doing this for their own plants that they own, right? Even though it's an Xcel-owned wind plant, they'd be bidding it in just like Next Air Energy would. Yes?
What's the reason why regions aren't happy?
As far as this method, you mean, or the whole market system in general?
Very well, but then in California, some of the reasons why they wouldn't.
Yeah, well, first of all, the question is, can you talk about why some regions aren't doing this as well, or accepting these methods? Different regions, like ERCOT in New York and California, and PJM out east, and New England all have ISO markets. They're all at different places in terms of penetration, how far along they are with this. Like New York does, have wind under a dispatch signal, but it doesn't expect you to follow it unless you're being curtailed. So you're really kind of a price taker there, and they'll give you a signal to turn down, but you're not really setting price as a market participant in the same way. I think they're all in different points in the learning curve in terms of that, about how fully they feel they have to incorporate wind into their market system at this point. And some of the markets work better than others just based on whether people are really trusting the market. And, California had problems with the whole Enron, the energy crisis, and there's a fundamental less of a trust in the market mechanism out there by some of the market participants. So that's a change. The bigger change, though, is that there's a lot of the country which isn't even in a market. There's a large portion of the West outside of California has resisted these market systems, as has the Southeast. Economically, certainly, I think people come out ahead when they go to these market systems. But there's a lot of very powerful utilities with a lot of investments they've made that they don't always want things to change. They don't want prices to change. So there's business reasons, there's political reasons why there's still resistance in some parts of the country to this. Ironically, some of the biggest resistances, like the federal government spent, hundreds of millions of dollars to build all these dam systems out west, like the Bonneville system in the Pacific Northwest. That's a government-funded project that's managed by a federal power marketing organization. Well, a lot of the local municipals, cities out there, are guaranteed very cheap hydropower from that project, like forever, And they don't want that that cheap hydro to go into a market and create a power market, because that would disrupt, their business model. So it's very complicated. The power system is extremely fragmented. Let me close by getting even a little more philosophical, because I've been talking with a lot of people about, we got a lot of work to do to improve forecasting, for example. And, who should be kind of responsible for that? Who should pay for that? Who should kind of lead that charge? Should it be the public sector, or should it be the ISOs, or, the government, the ISOs, the private sector, wind farm owner operators, who should do that? It's kind of two schools of thought the way I've been developing this, and this is fairly new stuff that we're just kicking around the industry right now. But one school of thought would say, look, reliability of the grid is a public good, right? We only can do it if we all work together. It's got to be kind of done at a a large, aggregate basis. And we know that the best wind forecasts are required if we really want to do the best job of reliably and economically incorporating a lot of wind energy, right? The better forecast that the system operator and the market participants have, the more transparency there'll be, the better we can run the system, the lower the average price to the ratepayer is likely to be. So that would follow logically then that, well, then wind forecasting should probably also be viewed as a public good, which would argue that, well, because the cost to society would be higher if the forecast is bad, it really makes sense if, that we in some sort of centralized way, either the federal government or the ISOs or somebody say, look, we just got to pay the money, we got to get the best forecast we can, we got to essentially give it to everybody, right? And so that would argue for these stronger centralized roles, or perhaps even socialized or more government funding of something like this. Well, that's certainly a valid point of view. I tend to like it, actually, but there's a whole other school of thought which says that we have these markets too, and this is always true. The grid operators need a forecast that's good enough to run the system reliably. But is it really their role to squeeze every bit of efficiency out of that? Isn't that really the role of the market participants to take care of optimizing the rest of this exchange? And shouldn't it be the market participants that actually pony up the money and the effort and the smarts to come up with better forecasts, figure out how to use that, and eventually that will kind of, you'll have the market will bring that all together eventually. And it's okay if the really smart power traders make some money in the near term when they're getting their better forecast and nobody else has it yet, things like that. Another perfectly valid point of view, but a very different one, right? Do you actually try to do this in more of a centralized basis that maybe is looking at, how do I lower the price of power for the average ratepayer? Or do I kind of let free enterprise and the market system just do its job? And that's okay if some of this money maybe goes to these traders, as they go through this process anyway. We're just having a lot of this discussion. If you guys have, I'd love to hear opinions on that too about what you think, because this really gets down to, I guess in some sense you can look at it in lots of other things too in the industry, like transmission policy, another very controversial issue. Should transmission policy be driven by the federal government so we end up with an interstate highway of kind of high voltage transmission lines, which would lower the average price of the average citizen? Or is it really more of a state by state issue, and these states are not really responsible for the national good, right? Which is closer to where we are today, by the way, where all the transmission is done state by state. If you look at all kinds of these things, it's a whole issue about, are you more a believer in, more of a more centralized public good argument, or are you more of a free market sort of person, I guess? So something to think about anyway. I'd be happy to take any other questions. I know we're about out of time, so a lot of interesting things. The point you ought to take away is that this whole industry, it's not only very multidisciplinary, as you're seeing with all your lectures this year. There's also a whole lot of very fascinating policy, philosophical arguments, different points of view, lots of vested interests, billions of dollars already invested in legacy plants that have to be taken into account, lots of utility companies that are all private investor-owned companies that have to fit in this. It's a messy but pretty fascinating place to try to change stuff. So plenty of room for whatever you want to do in the power industry. Thank you very much.